So we are here to present you our model for management strategy of a hydropower plant. Okay. So first, we want to discuss what is actually a hydropower plant. Then we'll tell you about the mathematical formulation, and finally we'll include the cost because we're not going to take them into account at first. Okay. So first, what do we call a hydropower plant? Well, a hydropower plant is a plant that produces energy thanks to the flow of water in a river. What are its parts? Well, we have the reserves. We have like a big reserve of water that is going to be made into electricity. Then we have the way to make it into electricity, which is the energy generation turbines. And then also we have all the wiring and all the electrical stuff, but we're not going to take it into account in this project. Okay, so now my colleague is going to tell you about the mathematical formulation of this project.
Thank you, Carlos. Now we have the part of the mathematical model. We have chose two kind of sets. I for the turbines and reserves assembles, and J for the days of the month. And because if you can see in this slides, they gave an example of the turbines and assemblers and a table of the prices of the electricity month. We have choice for the parameters and daily natural inflows, that is the M. Electricity price, that is the P. Maximum capacity of reserves, and that is the MC. The maximum daily production of turbines, that is the MP. The maximum monthly production of turbine, that is the maximum. The initial level of reserve, the O. And the final level of the reserve, that is the FI. Now, for the variables, we have choice different kind of. The daily energy produced each turbine, that is with the X1. The daily water spillage of each reserve, the S. And the level of each reserve will start at each day, the L. And so here we make an illustrate of each part of the variables in the picture. So if you can see, there is difference what we mean with the variables. The object function of this project is to maximize the benefit of this turbine. So we have the maximum of the production and the cost of production electricity. The formulation mathematical, we have the different subjects constraint. It's like the initial level of each reserve, that the level, the daily water equilibrium, the final reserve level of each reserve, the maximum capacity of the reserve, the maximum daily production of the turbines, and the maximum monthly production of turbines. Now, after this with this formulation, we get the results of our problems, and we get that it's best to produce electricity in the highest days that the price is very high of electricity. In the case one, and case two is we make an extra 10 daily gigawatt per hours production, and the results get that the prices of production we can come to 40 megawatts per hours of production of the best days to produce electricity. Now I give the word to Carlos to explain the other part.
Yes, also we have that when we add a maximum monthly production of a turbine, we get our first daily spillage, which is going to be in this case for reserve 2 if the maximum is for reserve 2. Anyways, for this first model, we have only taken into account the benefits. So our next step is going to be to include the cost. Why? Because we don't care if we produce 100,000 megawatts of energy if our costs are going to be higher than our benefits, because then it's not going to work for us. So what we want to do is add the cost into our model. See? Okay, so how does this change our mathematical model? First, in the objective function, we are going to include the cost. And we are going to include the cost in two different ways. We are going to include a variable cost, which will depend on how much energy we actually produce per day. And then we have a fixed cost. The fixed cost is going to be the amount of money that it costs us to actually start the turbine, like that. Okay, so SC is going to be the fixed cost, and this is going to depend on a new variable, which is going to be called Y, and will be 1 if our turbine is actually started on day J, or is going to be 0 if our turbine is not going to be started. And then we have the variable cost, which will depend on X. Okay. Then, as we have included a new variable, which is called Y, we have to define two new constraints, which are those that will tell us whether a turbine is actually started or not. Next step is telling you about the results. In this case, as you can obviously suppose, the benefits, the profits are going to be lower than the benefits that we obtained on the past example. But this is also a consequence of adding the costs. The costs that we have added at first are 50 or 70,000 euros in the case of fixed cost, and 3 or 2 euros per megawatt hour in the case of variable cost. But I mean, this can change. So we have discussed. So we are now going to discuss how the profits are going to change if we change this variable and fixed cost. When we raise the starting costs, we are going to see that it's going to be better in some cases to actually not produce any energy and throw just the water down the drain as spillage, than to produce energy. How is that possible? Well, if the money that you make is actually lower than the money that it costs you to start a turbine, then it's going to happen that. And then we are going to see what happens when we raise the variable cost. The variable cost, as you know, are the costs that come with the energy produced. So if you produce 1 megawatt hour, for example, you may pay 2 euros, but if you produce 100, you will have to pay 200 euros. Okay, so when our turbine is going to be better off not being started than being working in this case? Well, it's going to happen when the variable cost is actually higher than the price of the energy. Why is that possible? Well, because as you know, both the variable cost and the prices are going to be in the maximizing function multiplied by x. So if prices minus variable cost is higher than 0, then you're going to win money. But if this is lower than 0, then you're going to lose money, and then it's not worth it for you to start your turbine. So pretty much. In conclusions, what we have seen is we have discussed the strategies, and we have seen that they depend on each turbine and each reserve, and depending on their characteristics, on their maximum capacity in case of reserves, in the maximum energy production in the case of turbines. Then we have seen that it's not the same to look at benefits than to look at profits. Because in benefits, you're just looking at production. But when you're looking at profits, you're looking at the money you're making. And then you have to take into account the cost. And then, in the case of the cost, you have to differentiate it between variable and fixed costs, which operate differently and they don't affect in the same way. And then, finally, we see that a profit-based model is going to be better for us than a benefit or production-based model. So this pretty much wraps up the whole problem, and we hope you enjoyed it.
Thank you.